Okay, ladies and gentlemen, let's continue where we've ended our previous lecture, and that is with paragraph 12.7 on atmospheric and solar radiation. Just to summarize what we've done with the previous lecture, we've looked at solar radiation, and we said that there are two components. There's the sun, and then we have the direct solar radiation from the sun. And that would be a maximum in terms of if we have a surface like that with a normal, with 90 degrees angle in the direction with the sun. Obviously the sun moves throughout the day, and if we have a flat surface, then we do not get the normal radiation every day, except if we have a collector or something like that moves with the sun. So but in general, so we've got the direct radiation, and then we also have all the diffuse radiation of the atmosphere. And what is that? It is all the gases which is in the atmosphere, oxygen, CO2, ozone, etc. And all of them we can model it as a medium, not necessarily a solid as we've seen it before, where if there is radiation coming in, then a part will be absorbed, a part will be transmitted right through, and a part would be reflected. Okay, so most of those gases do not absorb a lot, but all of them reflect a little bit. And the fact that they reflect means that they reflect towards each other, and it's a big scatter that occurs. And we call that the diffuse radiation. So total solar radiation consists out of the direct radiation, and we have to compensate for the angle. And if the angle is 90 degrees, so if the sun is there, then we get the total component, because then the cos of 90 degrees is equal to 1. Okay, right. Now, in general, if we now look at the sun and the atmosphere, then we've done it with a previous lecture, and we've looked at the surface, then a certain amount of the sun would be absorbed, which is alpha. But then we have the atmosphere here, and what we're going to do is we are going to give the atmosphere a temperature. Okay, and from experiments it has been found that we can say the atmosphere is the same as another body, okay, with a certain radiation. And we give it in terms of empirical experiments. It has been found that typically T-sky would be 230 Kelvin on a cold day, and on a hot day it would be about 285 Kelvin. So that is typically the temperature of the atmosphere if we want to model it as a second body, okay, with its own radiation. Right, now, what is important is we've done Kirchhoff's law. Okay, and with Kirchhoff's law, what we're going to say is that that alpha is equal to the emissivity. Okay, that is an assumption, and it is an assumption that will work typically if the temperatures do not vary by typically 100 degrees Kelvin and more. And that is exactly the situation that we have with T-sky, the atmosphere, with most bodies. Okay. Okay. So if we want to look at what is being absorbed, let's call it E2. Okay, if we call that one 2 and that one 1, then we can say it would be equal to alpha of G sky. Okay, and that would be alpha 2. So let's call that alpha 2. Okay. So a certain amount of the radiation of this body is being absorbed. Okay, and we can say it would then be equal to alpha multiplied by sigma T sky. So we consider it as a black body. Okay. Alpha multiplied by Stefan-Boltzmann constant multiplied by T sky. So that would be the maximum that it can absorb. but it's a real body, a grey body, so therefore we have the alpha there. And what we then do is we say it is equal to the emissivity multiplied by alpha T sky to the fourth. Okay, so with Kirchhoff's law, okay, so what we do is we use Kirchhoff's law to say that alpha is equal to the emissivity of the body. And that we can normally measure with experiments, and we can measure it very accurately. Okay, so this is an assumption, but it is a good assumption. Okay. Right, now on this side, it is, if we look at what is being absorbed, it would be equal to alpha 1 multiplied by G solar. So let's call that one, where it was previously alpha S. You can still call it alpha S maybe. Let's do that. Or alpha 1, it doesn't matter. Okay. So if we now want to look at the net rate of radiation, the net rate of radiation on a body, because of atmospheric radiation, then we can say that the net rate in terms of a heat flux would be the sum of everything that is being absorbed minus the sum of everything that is being emitted. It's just an energy balance. Okay. So what is being absorbed? What is being absorbed is alpha S multiplied by G solar. Okay, so if we look at the sketch, a certain part of the radiation is being absorbed, okay, inside the body. Let's draw that in yellow. Okay. So normally a body on the surface, and we're talking now of maybe a piece of material or something like that, then a part will be absorbed. Okay. Now it might also be that this is glass or something like that, and then a certain part will be transmitted through it. Okay. But the fact of the matter is what is being absorbed at the moment, and that is alpha multiplied by G solar. Okay. And then what is also absorbed is equal to the emissivity multiplied by sigma multiplied by T sky. Okay. But then, is there anything else that we should add? That's the two components. Okay. What we shouldn't forget is that this body is also going to have a certain temperature. So if that is the temperature T is, because it has a temperature, it will radiate heat out. Let's call that E3. Okay. So what is being emitted is minus the emissivity multiplied by alpha, sigma multiplied by Ts to the fourth. Okay. So Ts is the temperature of the surface. Okay. And if we make the equation now a little bit neater, we can say it is alpha S multiplied by G solar plus the emissivity multiplied by the Stefan-Boltzmann constant multiplied by T sky to the fourth minus Ts to the fourth. The assumption here, very importantly, is that the body, the surface, the assumption of that is that the surface temperature is approximately room temperature. Now, many of you would now say, but that is not a good assumption. Okay. Okay, do you agree? However, with one of the previous graphs, I've shown to you that the alpha, as a function of temperature, it is a function of temperature, but the range of the graph is up to 3000 Kelvin. Okay. So if we consider room temperature, and we consider bodies that is being heated, okay, and we're talking of bodies like windows, the roof of your house, a solar collector, etc., then most of them will not go to temperatures of 100 degrees and more. So if you look at the range of the temperatures from 0 to 100, the function is not a strong function. It doesn't increase much. Okay. Okay. Just to give you an idea, we've taken some measurements again yesterday on the roof of Engineering 1. Erin, if you can look at the graph for me. So that's the radiation for the past 3 days. There are actually 4 curves on the graph. I know that the colors are not that good that you can see it, but with the previous lecture, I've shown you the different colors. And then you can see yesterday the solar radiation, the direct radiation was approximately 1,000 watts per square meter. Okay, makes sense, huh? Okay, and what you do not see very well is, but I'm going to put the mouse there, there is the green line. Okay, what is the green line? Is the diffuse radiation, which was about 100 watts per square meter. Okay, the diffuse radiation. All right, now I want to show you table A18. Okay. Now previously we've looked, typically, there you can see for different materials the emissivity, table A18. Okay. Now, there you can see the emissivity as a function of temperature. Do you see? So the emissivity there is always given as a function of temperature. And then you can look at typically the first one. Let's look on the right because you can see that properly. Magnesium polished. So if its value is typically about 0.07, so the temperature has to increase with 200 degrees Celsius before it would double the value. You see? Okay. And then if you look at nickel, now let's look at another example, maybe this third example here for that one there. If it's oxidized, that material, the temperature increases from 600 to 800, the emissivity will only increase from 0.80 to 0.82. Okay, so that is the argument. It's not a strong function. It is a function, but not a strong function. Okay. Right. Now something that you have to be careful for is that with this derivation, and in many cases, because we've derived this, and obviously when you do problems, you can every time develop it from first principles, you can do that. But, you know, after a while you get lazy, you know how the equation looks like, and you're going to use it like that. The one thing that you have to be careful for is that this was now derived with, let me write it here. No. Okay, so equation 1. So we will have the term T sky to the 4th minus Ts to the 4th. That term would be like that if the surface temperature is higher than the sky temperature. Okay. Okay. But in some cases you can get the opposite. Okay. So then this term will have to be Ts to the 4th minus T sky to the 4th. That would be if T sky is now larger than Ts. That you can also get. Okay, right. Now, a very, very important thing to remember, and that is that when we look at atmospheric radiation, what is the difference between that and all the other radiation that we've done as a build-up to what we're going to do now? So schematically, if this is now the sun, okay, and this is another body, let's call it body 1, then we know there will be radiation from the sun and there will be radiation from a certain body. Okay. Now the difference between the two is that everyone will have a spectral distribution. Spectral distribution SD, SD1. Okay. What does it mean? It means this spectral distribution is a function of the temperature of the body, but also all the different waves which is being generated at different wavelengths. Okay, so you will remember that we have this graph that typically looks like this. That was figure 12.9. If we can just go to that graph again. Right, Aaron, if you can just zoom in there on the graph. So that is for the emissivity as a function of wavelength. Okay. The radiation as a function of wavelength, and it is for a certain temperature of 5,800 Kelvin. Okay. Now other bodies will also have a certain spectral distribution. And these two are normally not the same. They will only be the same if this temperature is 5,800 Kelvin. And in our experience, or where most of you are going to work as mechanical engineers, in most cases that is not going to happen. Okay. So the temperatures are normally lower. So on the same graph, where previously we had this one of 5,800, in most cases, these bodies, body 1, is going to be there. Okay. So most of the bodies, in terms of radiation, is infrared radiation. Infrared, while in this case we have what we call solar radiation. Solar radiation. Right, so if we are interested in the radiation on a body, and here we've got another body, then what is important, we've said, is that the alpha of the bodies is a function of that temperature. It is being influenced by that temperature. Okay. So there's alpha 1 and there is alpha 2. So for us as engineers, it would mean that we need information on the alpha or the emissivity of objects, because then we can do designs to determine the net rate of radiation. The practical problem that we have is on this side. There's almost an infinite possibilities. So every other body, body 2, is going to have another spectral distribution, which is not going to be the same as this one, and it is going to have another alpha. So for every one of them, we will have to generate data. Okay. Now, in many specific applications in industry, that will be generated and it will be available. But it is just too much trying to put it in your textbook. It is overwhelming in terms of the information that you need. But there's one that is special. And the one that is special is this one. Okay, so this one is a special one. So for that reason, if you go and look in table 12.3 in your textbook, table 12.3, let me put it up for you. Right. In table 12.3, if we can look at it quickly, it gives a comparison of the solar absorptivity alpha S of some surfaces with the emissivity at room temperature. Okay, at room temperature. At room temperature. So it gives us alpha S, which is called the solar absorptivity. The solar absorptivity, and then it gives its value of emissivity. However, what is important is it says that that value is at room temperature. Okay. So, if we want to do the designs or consider solar radiation on surfaces, and we want to use, excuse me, and if we want to use a table like this, Erin, if you can just zoom in again, we can use all those values, but we will have to remember it would only be valid if the surface temperature, the order of magnitude is about at room temperature. Okay. So, let's look at typically of some of the values. Okay. What is interesting? Let's look at aluminium that is polished. If it is polished, then the solar absorptivity is 0.09 and the emissivity is 0.03. Okay. Okay. And then, if we look at black nickel oxide, then the absorptivity is 0.92 and the emissivity is 0.08. What would the application be of this material? A good application would be a solar collector, because you want alpha to be high, you want to absorb heat. Okay? And black paint, okay, black paint, 0.97. Okay, but the emissivity can also be 0.97. Okay, so although it can absorb a lot, it also radiates out a lot. Now, paint is a very, very complicated issue in terms of solar applications. The general rule sort of is if you use white paint, it would reflect, and if you use black paint, it will absorb. And in general, it is true, but you can also end up in this. So, paint is a specialty area on its own. NASA developed paint, a very special paint. They first started developing that for the Challenger coming in in terms of the tiles that was used, and since then a lot of work has been done on it. So in general, if we want to design solar collectors, the absorptivity, the solar absorptivity should be as high as possible, but also the emissivity should be as low as possible. Okay? Then for other types of applications, like maybe fuel tanks or refrigerator trucks, in those cases you want alpha to be as low as possible, and you want this one to be as high as possible. It must radiate out as much heat as possible. Okay, now in terms of just coming back to what we previously have done, this is the Earth, and that is the atmosphere there, typically 30,000 meters, and there's the Sun. Then with the previous lecture, I've indicated that if you've got a surface there, in terms of radiation, and that is theta. Okay, so if this would be normal to the Sun, so if theta is equal to 0, then GD, the maximum radiation, would be 1,373 watts per square meters. Okay. I forgot to point out with the previous lecture that that is the average. Okay, so that is the average. On the 3rd of January, okay, then the Earth is as close as possible, then it is the closest to the Sun, 3rd of January, and then that value would be about 4% higher. So then it would be 1,418, so that would be the maximum value of it on the 3rd of January, and on the 4th of July, it is the farthest away, and then it is 1,325. So that's the range, but that is the average that you can get. Right, so let's start getting a little bit more practical. We're almost going to start doing problems. So in general, if we look at solar radiation on a surface, there's a surface, and there's the sun. Okay. Then we have what we call direct radiation. So that's the first component of our radiation. Then we have all the radiations that reflects from everywhere. We put it together as one component, and we call that the diffuse radiation. Diffuse radiation. Okay, and then there's another one that is a little bit of a complication, and that would be reflections from other bodies. Maybe a tall building or something like that. So that's the three components: direct, diffuse, and reflection. The third one is very difficult if you have to design for it, okay? Because it would obviously now depend on where the surface is. If you take this surface, move it 1 kilometer away, then obviously you can reduce the reflection, but then there might be other trees or other objects in the region that will also reflect on it. So it's a very difficult one to design for, but you can measure it. Okay. But in general, this body here that I've drawn like that, which is just a principle that I want to show, can be, for example, grass. So if it is grass, trees, rocks, and concrete, then a typical, just order of magnitude value is that they would reflect about 20% of the solar radiation. So about 20% will be reflected. Now that 20% obviously is reflected in all different directions. Everything is not reflected to this one surface. Okay. Then other objects like snow. If it's covered in snow, then it would reflect about 70%. So the reflection of snow is very, very high. Okay. Glass. Glass is very important for us as mechanical engineers because normally we are the guys that have to design the air conditioning systems of buildings. Okay. Now glass typically would, we know, would absorb a certain amount, would transmit a certain amount, and would reflect a certain amount. So if it is uncoated glass, then about 80% would be reflected. Just about 8% would be reflected. And the toll that goes through would be about approximately be 50%, just an order of magnitude. Okay. And being absorbed, depending on the type of glass, can be 55 to 50% that is being absorbed. In your textbook, if you go and look, you'll see that there are many different types of glasses. Okay? So glass itself is a very specialized field, but it is an important one because of the following reason. And that is that, let's suppose there is a glass there, and here's an object here. Okay. Another object. And maybe this object might be a solar collector. Okay. So as we say that the glass would transmit a certain amount of radiation through. Okay. Now what will this object do? It will also reflect. Okay. So what is coming in, a part would be reflected. Okay. And this reflected, if only 8% is reflected, it would mean that most of the radiation would just go back through the glass. Okay, that is the normal argument for this. But glass, as I've said, can be very, very complicated. There are glasses, the glass depends in terms of how much goes through, depends on the properties of the glass, and now very specifically the wavelength. Okay. So there is glass available that would allow almost all the radiation going through, but then when the radiation comes back, if we look at that wavelength, which is obviously a large, let's call it from 1 to n, all the wavelengths of the solar radiation coming in, a large spectrum of it. What this glass will do is most of this wavelengths will not go back. Okay, it is trapped. Because the wavelengths here is now from N to Z. So the wavelengths change, and because the wavelengths change, the radiation can't go back. Okay, and what in any case is being reflected then is just coming back. So these types of glass are specifically good glass, or glass that should be selected if you want to trap heat. Okay, so if you want to trap heat, then you have to go and select those glasses. Very, very specific glass. Right, let's start doing problems at last. Practical problems. Okay. The problem that we're going to do is 12.69 in your textbook. Okay. Now that problem says solar radiation is incident on the outer surface of a spaceship. Okay, so a spaceship at a rate of 1,200 watts per square meter. The surface has an absorptivity of 0.1 for solar radiation and an emissivity of 0.6 at room temperature. The outer surface radiates heat into space at 0 Kelvin. So the space is at 0 Kelvin. If there's no heat transfer into the spaceship, determine the equilibrium temperature of the surface. Okay. So we have a spaceship, which means here's the Earth, and here is our atmosphere at 30,000 meters, and this spaceship is out of our atmosphere. So there is the spaceship, and let's model it as the outside in terms of a plate. Okay. Okay. So what this spaceship would experience would be G solar, which is from the sun, okay, and alpha S has been given as 0.1, and G solar is given as 1,260 watts per square meter. Okay. Now, if it was a body inside the atmosphere of the Earth, then we would have also had the component of the diffuse radiation, which in this case we do not have. And that diffuse radiation will be from a body at a temperature T sky. In this case, we do not have it because it's outside of the atmosphere. Okay. Right. What else we will have is that this body will have a certain temperature, okay? And let's call the temperature Ts for the surface of the body, of the spaceship. Because the spaceship will have a temperature larger than 0 Kelvin, we hope, it will radiate heat to T sky, which is at 0 degrees Celsius. And the emissivity of the body is 0.6. Okay. And we can consider the body as if it is insulated. Why? Because they say if there's no heat transfer into the spaceship, okay, so there's no heat transfer into the spaceship, okay, so we can consider it as if it is insulated on this side of the body, the inside of the spaceship. Okay, so this plate, we can say that is the temperature outside of the spaceship. Right, it's just a normal energy balance. The heat transfer in would be equal to the heat transfer out. Okay, the heat transfer in would be alpha S multiplied by G solar. Okay, and what is going out? What is going out is the emissivity multiplied by sigma multiplied by Ts to the fourth minus T sky to the fourth. Alpha S is equal to 0.1. Okay. G solar is equal to 1260. The emissivity has been given as 0.6. Sigma is the Stefan-Boltzmann constant, which is 5.67 multiplied by 10 to the minus 8. Okay. Then Ts is actually what we want to solve. Ts minus T sky. And T sky is at 0 Kelvin. So it is to the fourth. Okay. Coming back to this equation that we've derived, do you remember? T sky minus Ts, in some cases you will have to say Ts minus T sky. Okay. And this is such a case. Okay. So it is now very easy to solve the temperature of the spaceship as 247 Kelvin. Okay. 247. Now if this value of the emissivity of the spaceship was found from tables, such as the one that we've discussed just now, we can see that the temperature, the order of magnitude is approximately room temperature. Yep.
So the temperature of the sky, is that 0 degrees Kelvin or 0 degrees Celsius?
Kelvin. T sky is 0 Kelvin, so it is out of the atmosphere. There's nothing, sort of a vacuum. So it is 0. It's not a very realistic value, but this is now what has been given for us. Just something to play with. Right, 12.
Question. You said TSS and T sky there. Are they supposed to be switched around?
You can switch them around, so just be careful for it.
The following equation on the right, you don't correlate with the equation on the left.
The equation on the right doesn't.
You said T sky is greater than TS, so use that one. Is the TS4 minus T sky more than S,
Yeah, I hear what you say. You're right.
In the yellow at the bottom, number 2, sir.
Yes.
Over there, Ts to the fourth, yeah, that's incorrect according to the equation.
You go to the right of that?
Yes.
So that's supposed to be the other way around.
Yes. Okay. Sorry. So this should be the other way around. Okay. I've just written it wrong. Okay. Good. Right. 12.70. The next problem. Right. 12.70. A surface has an absorptivity of 0.7.
So that equation was right, but what happens is you take that to the other side of the equation and it's that swaps around.
Okay, it's fine. Okay. Okay. In many cases, I think the thing that you have to be careful for is don't always just use the equation just as it is. Maybe you can just solve it from first principles. It is really not that difficult. So if I would be you, just look at what is being absorbed minus emitted. Write out the 3 terms. 3 terms can be reduced to 2 terms. Okay. Right. 12.70. A surface has an absorptivity of 0.72 for solar radiation and emissivity of 0.6 at room temperature. The surface temperature is observed to be 350 Kelvin when the direct and the diffuse components of solar radiation are GD 350 and G small d, the diffuse one, is 400 watts per square meter respectively. and the direct radiation makes a 30-degree angle with the normal of the surface. Excuse me. Taking the effective sky temperature to be 280 Kelvin, determine the net rate of radiation heat transfer to the surface at that time. Right, problem 12.70 in your textbook at the back. Okay, so schematically we can say, right, here's the surface. Call that temperature T surface. And it is 350 Kelvin. And there's the sun, and the sun radiation GD is equal to 150 watts per square meter. Okay, that angle is 30 degrees. Okay, so it is not at 12 o'clock yet, maybe 9 o'clock in the morning, something like that. And on this side, schematically, we have the diffuse radiation, which is 400 watts per square meter. So most probably a very cloudy day. Okay. And they give us that T sky is 280 Kelvin. And the emissivity of this surface is equal to 0.6. And the alpha S is equal to 0.72. Okay. Let me just read the problem again to you while we look at the sketch. A surface has an absorptivity of 0.72, there it is, for solar radiation, and an emissivity of 0.6 at room temperature. The surface temperature is observed to be 350 Kelvin, so it has been measured, when the direct and the diffuse components of the solar radiation are 350, sorry, so this must be 350, not 150, and 400 watts per square meter respectively. And the direct radiation makes a 30-degree angle with the normal of the surface. So there's 30 degrees. Okay. Taking the effective sky temperature to be 280 Kelvin, determine the net rate of radiation heat transfer to the surface at that time. Right. So, in terms of radiation, G solar, the solar radiation on an object would be the direct minus the multiplied by the cos of theta plus the diffuse radiation GD. Right, GD is equal to 350 multiplied by the cos of 30 degrees plus 400. Okay. And that would be equal to 703.1 watts per square meter. Okay? So if we look at the two components, 350 and 400. So potentially that can be 750. When will it be 750? When the cos of theta is equal to 1. And that would be when that angle is equal to 0 degrees, and that would be 12 o'clock typically in the afternoon. You getting? Okay. So that would be the solar radiation onto the surface. So let's look at this surface in terms of what happens on it. So if we look at that surface, what happens is that we have 703 watts coming in. Okay. But we also know that because it has a temperature of 350, it will radiate heat out. Okay. So what is being emitted would be sigma multiplied by the surface temperature to the fourth minus T sky to the fourth. Okay. So the sky is being seen as another body. The radiation to another body, and in this case the other body is at 280 Kelvin, so the radiation would go out to T sky. So, excuse me. If we calculate it, then it would be 5.67 multiplied by 10 to the minus 8, The surface temperature is 350 Kelvin to the fourth, minus T sky 280 to the fourth, and the result is equal to 492.5 watts per square meter. Right, so that going out would be 492.5. Okay? Yep.
So what about E?
What about E?
The coefficient.
My goodness, yeah, sorry, I forgot to put it in here. Forgot to put it in there, so it should be there. And then that should obviously have the value of 0.6, which should also be in there. And I think my calculation is correct. I just forgot to put in the emissivity. So 703 coming in, 492.5 going out. So the net rate of heat transfer would be 703.1 minus 492.5, and that would be equal to 205 watts per square meter. Okay. So the surface area hasn't been given in terms of the number of square meters. If that was the case, we can just put in the surface area there, or we can do all the calculations for 1 square meter and then later on just multiply it by the number of square meters. Elsemarie, you do not look happy. Anything wrong?
I was wondering about the solar electricity. Isn't that coming?
Yes, I forgot to put it in. So this one is here.
I mean alpha.
Oh, right. Okay, sorry. Okay, guys. Okay, sorry. Let's start all over. Okay, sorry. Okay, sorry. Okay. Right, so the energy coming in would be equal to alpha S multiplied by G solar. Okay, so alpha S is equal to 0.72 multiplied by 703.1. Is that right? Okay. Can somebody just calculate for me what this value is? $703.1 multiplied by 0.72. 506.23. Okay, watts per square meter. Okay, right. Okay, so what is going out? Would be equal to the emissivity multiplied by sigma S. Emissivity multiplied by that. T is the temperature of the surface to the fourth minus T sky to the fourth. Okay, and the emissivity is equal to 0.6 multiplied by 5.67 multiplied by 10 to the minus 8. Surface temperature, okay, hasn't been given to us. How much? 350, okay, so I'm so confused today. Okay, 350 to the fourth minus T sky, which is 280 to the fourth. Okay, answer? Somebody can calculate? 301.41 watts per square meter. Right, so The net heat transfer would be equal to 506.1 minus 301.4. And it's the same answer as previously, is that right? Okay. All right, 205 watts per square meter. Right. Okay. Okay, ladies and gentlemen, thank you very much. I will see you then later on today for the second lecture, and then we will continue with 4 more problems if we have enough time. Okay, thank you very much.